Witamy na drugiej prelekcji czwartego dnia na Tygodniu Mózgu Maria Myśli na UMCS. Naszą prelegentką jest dr Kaja Jasińska. Dr Kaja Jasińska jest adiunktem w Katedrze Psychologii Stosowanej i Rozwoju Człowieka w University of Toronto oraz dyrektorem naukowym Laboratorium Brain Organization for Language and Literacy Development. Głównym obszarem jej badań są mechanizmy neuronalne, które wspierają rozwój językowy, czytelniczy i poznawczy w ciągu całego życia. Badania te mają na celu zrozumienie, w jaki sposób wczesne doświadczenia życiowe mogą zmienić zdolność mózgu do nauki języka i uczenia się, szczególnie w środowiskach zagrożonych ubóstwem. Co warto zaznaczyć, dr Jasińska oprócz współtworzenia ponad 40 publikacji naukowych jest współtwórczynią Allo Alphabet, programu EdTech na telefony komórkowe, który dostarcza lekcje czytania dzieciom na obszarach wiejskich Wybrzeża Kości Słoniowej. Dr Jasińska przedstawi wykład zatytułowany Neurobiology of Language and Literacy – Insight from the Bilingual Brain. Zapraszamy do zadawania pytań na czacie YouTube i na e-kursach, na które dr Jasińska odpowie po wykładzie. Wykład odbędzie się w języku angielskim. Zapraszamy do słuchania. Welcome to the second lecture on the fourth day at Brain Week, Maria Thinking at UMCS. Our lecturer today is Dr. Kaja Jasińska. Dr. Kaja Jasińska is an assistant professor in the Department of Applied Psychology and Human Development in University of Toronto, and the scientific director of the Brain Organization for Language and Literacy Development Laboratory. The main area of research is the neural mechanisms that support language, reading, and cognitive development across the lifespan. This research seeks to understand how early life experiences can alter the brain's capacity for language and learning, particularly in communities at risk of poverty. Of note, in addition to co-authoring more than 40 scientific publications, Dr. Jasińska is the co-creator of Allo Alphabet, a mobile phone edtech program that delivers reading lessons to children in rural areas of Ivory Coast. Dr. Jasińska will give a lecture on Neurobiology of Language and Literacy, Insights from the Bilingual Brain. We invite you to ask questions which Dr. Jasińska will answer after the lecture. Enjoy listening. And the floor is yours.
Thank you so much. Dziękuję serdecznie. Thank you for the invitation and for allowing me to join you even virtually here from my home into Poland to share with you some of the work that I've been doing over my career. Both spanning from when I was a doctoral student many years ago to some of the research that my laboratory is doing currently. And so we're going to focus on neurobiology of language and literacy and see what we might be able to learn from the bilingual brain and the bilingual experience. So arguably, our most human thing that we do is language. No other species even comes close to what a human child can do when they're communicating with language. And in fact, we've had this ability for a long time. Language is perhaps 150,000 years old, perhaps even older than that. And it's no surprise then that also no other species learns to read. And this is intuitive because reading really depends on language. But unlike language, which we could argue we've got a very strong biological kind of disposition for learning, reading has to be explicitly taught. And reading has actually only been around for about 5,000 years. And so these two aspects, language and literacy, are really interesting to look at together because they sort of point to some of the biological systems that through evolution our species has been endowed with, and also some of the ways in which something new like reading, a new technology, can make use of those existing systems and support us and support children as they learn. Now, of course, a human child has no idea what language they might be born into. And so they've got to have an ability to learn any language that they might be exposed to. And they do so irrespective of what that language might be and of all the linguistic variation, that really spectacular linguistic variation that exists in the world. Babies tend to learn language on a near identical maturational timetable. They hit their first word around their first birthday. They start combining words together around when they're 18 months and so on and so forth. And they seem to reach this across all languages. So how does a human do this? how is that language represented and processed in our brain? Well, this bilingualism actually gives us a couple of clues. And that's because there is tremendous variation in the bilingual experience. Individuals differ with the age at which they became bilingual when they learned their first and second language, the differences between their two languages, whether they might become literate in one or two languages or just their first or their second. And they might actually be bilingual in languages that span different modalities, right? So you could have an individual who learns a sign language, an individual who learns a spoken language, or who might even be accessing a spoken language through a cochlear implant. And so if we can scientifically probe some of this kind of naturally occurring variation in language, that might help shed some light on how language might be organized in the brain. So we're going to explore some of these things today. And we're going to start off by talking a little bit about some of the neural systems that make language and literacy possible, and how we get from a small baby up through childhood and into adulthood, learning our language and learning how to read. So we're going to start off with just thinking about what it is that we know when we know a language, right? So here we've got a cat, and when you're a speaker of English, you know that the sounds k, t together stand in for this animal, right? That's really what you know, is that there are sound patterns that refer to some real world, referent out there. And as you learn to read, one of the things that you acquire is understanding that there's a written form. And so a series of curves or lines or squiggles on a page actually stand in for those sounds, the k, t, and stand in for this particular referent, the cat that your household pet or whatever you might have. And so these are really kind of the important sources of information that we have to reconcile. It's really symbolic representation for certain sounds standing in for an entity, and then certain graphical representation standing in for those sounds and standing in for those entities. So how does this actually take place? How does a child learn to kind of acquire this whole system? Well, there's a very typical developmental trajectory. And if we think about kids progressing from pre-readers, those that aren't reading yet, to ones that are in the emergent stages, and that's really, if you have a small child or have ever seen a child or taught children, you know that at the earliest stages of reading, this is a very laborious process for them. They're working their way through sounding words out letter by letter. And at some point they arrived at what we would call more skilled and fluent reading, where they're reading with a lot more automaticity, the way you and I are. Now, before a child even learns to read, they already know that they're already very proficient speakers of their language. They already know that there's this symbolic relationship between sound and some referent. And as you begin to learn to read, at first there's a lot of work around learning the connections between individual letters, at least for alphabetic languages, and the actual spelling of the word, the orthography. But at some point, you become more of a proficient reader, and you could do this with a lot more automaticity, the way you and I do when we're reading. We're at the point where you almost can't help yourself but extract meaning when you see printed language, right? And then to think that there was a point in your life where you didn't know how to read, and this was a very arduous task, to the moment you are today, where words appear in front of you and you can't help but get meaning out of that. It's actually kind of remarkable. Kind of pause and think about this. And so I'm really interested in how that takes shape. And so these kind of aspects, we can think of this as a kind of a model that involves the sound patterns or the phonology, the meaning or the semantics, and the writing system or the orthography, right? So we can think of these three components as being really critical domains. Now, how does your brain do this? So here I'm showing you just a left hemisphere and a right hemisphere view. This is kind of the front and the back of some of the key regions that are associated with supporting these processes. And one thing that you can note is that this is really a largely left hemisphere network that supports language and supports literacy. And one of the things you'll note is that here in blue, we've coded regions of the brain that seem to selectively respond for language in its printed form, so written language. And you can see a lot of blue regions here in the back of the head and the occipital lobe. This is a region of the brain associated with visual processing. And so it really follows that, printed language being visual engages regions of the brain associated with visual processing. In green, we actually have regions associated that are selectively responsive to speech. And here we see a lot, at least in the left hemisphere here, a lot of green activity or green regions in this portion called the superior temporal gyrus, which is a part of the auditory cortex. And so it's a part of the brain that helps process sounds, including the sounds of language. But what's really striking is that there's a lot of overlap. Right? There are a lot of regions, even particularly here in the inferior frontal regions, where there are the brain is responsive to language irrespective in both its forms, in printed and in spoken form. And so some of those key regions are the inferior frontal gyrus. This is a region that's classically associated with kind of the search and retrieval of meaning through our mental dictionary or lexicon, among a whole host of other functions. The superior temporal gyrus, which is very much linked with phonological processing, so processing the sounds of language, the sound patterns of language. Up here, another key region that we're going to see today is the supramarginal. This is a region that's been implicated in making mappings between letters and sounds. And then we've got some dedicated regions in the posterior portion here, chiefly the visual word form area, or the VWFA. And this is a region that seems to be selectively responsive to words in their visual form. And of course, you've got that very important overlap between the print and speech networks. So what do we already know about kind of a child's transition and how these structures come to be, especially that region of overlap? Because when you're born, you don't have any regions of the brain that are specifically tuned to reading. You have to learn this. So there's some changes, both developmental and as a function of that experience, that are going to take place over that childhood trajectory. So I'm going to tell you what we know already about a pre-literate brain. And actually, for some of the studies that I'm going to share with you today, I'm just going to put the details here in a little box. So I'm not going to go into this in too much into the nitty-gritty of exactly how we did and the various manipulations. I want to give you kind of a big picture, highlight some of the key things, but I'm always going to put the details here. So in this particular study, we compared a group of kids, 4 and 5-year-olds who hadn't yet started any formal literacy. So we wanted to look at what this pre-literate brain was doing and compared these kids to a group of emergent readers who were 6 and 7 and had already started reading. And these kids completed a neuroimaging task, and you can see an image here. Actually, all the studies I'm going to share with you are going to be using this technology, and this is called functional near-infrared spectroscopy. I'm not going to go into it in too much depth, but would really love if anybody had any questions about it. I'm happy to spend some time talking about it in that question period. fNIRS for short is in many ways very comparable to fMRI. And so we're able to look at brain activation using the system, but it uses a cap of little lights that's placed on top of the head rather than a big magnet. So it's a little bit different in its mechanics, but essentially a lot of the images of brains we're going to see can be interpreted in a manner analogous to how you would interpret an MRI image. One of the things is that, for kids, especially 4-year-olds, this is a really nice and friendly system because you just wear it, you could sit upright, you don't have to go inside the scanner. And so it's got a few important advantages for developmental research. So while our kids were wearing this fNIRS system and we were looking at their brain activity, we had them listening to and reading words. Now, our pre-readers weren't reading words yet, they're pre-readers, but only our emergent group was doing that. So I'm going to show you what we found. So for our pre-literate kids, when they were listening to words, I'm showing you here the left hemisphere, we see very nice kind of canonical activation in that superior temporal gyrus region. We actually see it in the right hemisphere as well. I'm just only showing you the left here. And this is not a surprise. It's exactly the regions of the brain that we expect to be active when you're listening to language. So there's nothing new here, but kind of proof of concept almost. But when we look at kids who are in an emergent stage of reading, when they're doing the identical task, right, they're still listening to words, we're still seeing this really nice superior temporal gyrus STG activity, but we're also seeing a lot of robust activity in the IFG. And this is really interesting because it seems that over this developmental transition, we see a little bit more recruitment. And if you look at how these kids' brains process printed language, a lot more activity in this inferior frontal gyrus. And so we're sort of seeing that neural activity for spoken language, for speech itself, changing as a function of development, so changing as kids get older and in response to their reading experience, such that the sprint and speech activity starts to look more similar. Okay, so what about when you swing a little bit upwards and look at kids becoming a skilled reader? We're still talking about emergent readers who are just at the cusp, 6 and 7-year-olds. So here what we did is we extended our work to a group of kids who are now older. So we had our young readers, and then we added a second group of more skilled readers. And they did a similar neuroimaging task using the same technology. But in this case, they were reading words that were regularly spelled and irregularly spelled. And this is actually an important distinction for English in particular, because English has a lot of these words that are irregularly spelled. So what do I mean by this? So a regularly spelled word sounds exactly how it looks. You can sound it out letter by letter and you can arrive at the correct pronunciation. Irregular words are kind of these exceptions. And so the spelling is not all that, doesn't correspond to sound in a really one-to-one or very predictable way. Some languages tend to have only regular spellings. Polish is one like this. You don't have irregular words really. English tends to fall sort of along this line. But the existence of these kinds of word types allow us to sort of exploit some of the processes that go into reading, because when you're reading a regularly spelled word, you can sound it out letter by letter, and you can really rely on your knowledge of phonology to do so. But you can't really arrive at the correct pronunciation of an irregular word while doing the same thing. Instead, you really just need to learn these words. You just kind of have to know them. And so being able to access words directly from your lexicon, from your mental dictionary, is really going to be more important for reading these irregular words. So what we did is actually compare brain activity across these two conditions. We looked at this first in our really young emergent readers. And so what you're seeing here is areas of the brain that had more activity for the irregular word type relative to the regular. And one thing you'll notice, there's not really that big of a difference. If anything, we see a little bit of difference in the supramarginal region, which is interesting because it's a region associated with letter sound mapping. And so at a time in a child's development when they're really, relying on letter sound mapping, we're even seeing a little bit of activity there, even when we read these irregular words. Now, the really interesting thing that happens is when you become a skilled reader, actually we see a really big difference between these irregular and regular words. Irregular words very much tend to recruit this inferior frontal gyrus, which we know to be associated with lexical access. And so we're really seeing like a focal brain correlate of a developmental reading milestone. And we can see how different regions of the brain support different aspects of language processing in its printed form as a function of development and of that experience. So it gives you a little bit of a snapshot or some of the regions that are implicated and how they might change over development. But of course, we want to know about the bilingual impact, right? When we're just thinking about those monolingual children, it's important to consider, at least point out, that monolingual individuals are kind of the minority worldwide. Most people learn multiple languages. And so we really want to understand to what extent some of those neural substrates are and developmental changes in those substrates are universal, and to what extent bilingualism might impact. So I'm going to start off by telling you about bilingual babies. So right at the very beginning. Now, really amazing thing about babies, really the first year of life is a tremendously rich and exciting time in terms of language development. But all babies, irrespective of what language they're born into, have what we would call universal phonetic discrimination. That means that they can tell apart all of the sounds of all of the world's languages. So kind of classic example is in English, we have a l and r sound, the L and the R, that we don't actually find in Japanese. So Japanese adults really struggle with the l and r sound if they're learning English later on in life, but Japanese babies, even if they've never heard English spoken before, can actually tell these sounds apart. So prior to about 6 months, infants have this universal phonetic discrimination, but that ability tends to wane such that by the time they arrive at 12 months, they only discriminate the sounds in their own language. So what we wanted to understand is, well, how does this, what are some of the neural components of this process? And do they operate similarly in monolingual, bilingual infants? If you're exposed to more than one language, you're learning to discriminate different language sounds across 2 different languages. You've got 2 of these to contend with. And so might that have some impact on how your brain manages to reconcile this information? So what we did in the study is we outfitted our babies with our FNIR system to measure brain activity. And we had infants listening to language sounds in their native language, which was English for all kids. And we also had kids listening to language sounds in a non-native language, a foreign language they had never been exposed to. And crucially, even for our bilingual participants, kids they were bilingual in some other language. So our non-native language was one none of the babies in the study heard. So here's what we found. We looked at a difference between how the brain responds to your own language versus one you've never heard at a time in kind of around this 12-month milestone. So for an older group of infants. I'm just showing you a couple highlights from this study. So focusing on this older group. And actually both groups of babies show more activity in these left hemisphere language areas for their native language. And so that's really nice because we know they're honing in on their language and discovering the structure of that language. And we see again the sort of focal brain correlate of that developmental milestone. But an interesting thing happens with the bilingual babies. Our bilingual babies actually seem to show some additional or a longer period of neural sensitivity for non-native languages. So when older bilinguals are listening to non-native languages, things they've never heard before, they seem to show a little bit more activity in some of these phonological processing regions. And this is really interesting because it's now across a couple different studies well replicated that bilingual babies actually maintain this universal phonetic discrimination ability a little bit longer in development than monolingual infants do. So at a time when the monolingual infant has already lost this ability, cannot discriminate foreign language sounds, the bilingual infant can still do this. And that seems to be at least partially supported by regions in the superior temporal gyres, which are associated with processing phonology. So that's an interesting difference between monolinguals and bilinguals. And we're going to shift all the way up to school-age kids from that, but I want to kind of hold on to this sort of difference because it's kind of a little kernel that might underpin a lot of the other things that we observe. So this is actually a really large study we did in Toronto about 10 years ago. We had all sorts of different bilingual groups we were comparing, but I really just want to focus in on early bilinguals. So these were kids who learned English and some other language from birth. Now the study was done in Toronto. Toronto is an exceptionally multilingual place. And so we have an abundance of bilingual babies where, mom might speak one language and dad might speak another language. And so a child ends up growing up learning 2 languages from birth. And so we had kind of all these different bilingual and monolingual kids as well. And this is a kind of a study we did in schools where we measured children's phonological awareness. So how their awareness and ability to manipulate all the sounds of their language. And this is actually a really important predictor of reading skills. So how well you know the sounds of your language and are able to manipulate them tends to be overwhelmingly the biggest predictor of how well you read. So we measured this phonological awareness, vocabulary, and we had a series of different reading tests for our kids. And what we found is that these early exposed bilinguals actually outperform monolinguals, specifically on measures of phonological awareness and in reading. So there seems to be, an advantage conferred upon a bilingual child, particularly a bilingual child who's exposed to 2 languages from birth in the domain of phonology. And sort of follows that perhaps some of those differences we observed in infancy might actually have a role here. Now, this bilingual advantage in language and in reading has been replicated elsewhere, including recently in some of our research in Côte d'Ivoire. And I'll just, one of my doctoral students, Mary Claire Ball, did a lot of wonderful work on exploring that. And if you're interested, you can check out our paper here. If you have questions about my work in Côte d'Ivoire, I hope I'll have a chance to talk about it. I'm not going to focus on it too much today, but happy to answer any questions about that. So even in Côte d'Ivoire, bilingual children showed advantages in phonological processing and reading when we explored that there. So there is a difference in how bilinguals are learning to read. They seem to show this advantage. What might some of the neural mechanisms be that support that? Well, we went ahead and did another study with, again, that sort of emergent and skilled group of readers, but now we've got both a monolingual group as well as a bilingual group. And these are bilingual kids who are bilingual from birth, so speaking 2 languages from birth. And so they're very proficient in both of their languages. And they did that same reading task where they're reading these regular and irregularly spelled words. And so one of the things we did is just compare brain activity between the bilingual and the monolingual. And what we found is that the bilingual child at the emergent stage just shows more brain activity than the monolingual child. And actually, we see more activity in this superior temporal gyrus region that we know is associated with phonological processing. We see additional activity in the right hemisphere and even additional activity in the frontal lobe. And this pattern holds true even when kids become skilled readers, right? So the bilingual is still showing more activity than the monolingual child. And now it involves more of the inferior frontal gyrus, which follows because we know skilled readers are relying a lot more on that region later on. But again, more activity for the bilingual child. So they're showing more neural activity, but the question is why, right? So there seems to be a language and reading benefit for bilinguals. They're showing more brain activity, including in some of those really important left hemisphere language and reading areas. We wanted to understand this a little bit better. And so we thought, why not probe some of the variation in being bilingual? So perhaps something about when you became bilingual might shape some of those differences in brain activity. So what we did in this study is actually add in a group of early bilinguals, again, same kind of cohort, learning 2 languages from birth, but we added a second group of later bilinguals. And these are kids who spoke English from birth and then learned French at age 5. Or right about age 5. Now, these are not late bilinguals. I'm using quotes for this group. If you've learned English or you've learned your second language at age 5, you're probably an extremely highly proficient speaker of that language. You're not a late bilingual by any sense, but really it's just to sort of denote the difference between these 2 groups. And in this case, we had kids doing a sentence reading task. And so what we did is we actually compared brain activity for these later bilinguals and early bilinguals. And what we found is actually the later bilinguals seemed to show more brain activity. And while there was certainly some activity and some additional activity in the left and right hemispheres, this was disproportionately observed in the frontal lobe. So it seems as if later bilinguals show greater frontal lobe recruitment. But the important thing is they do this in their first language. So this is a reading task in English. English is the first language for all of the kids in the study. So this isn't because they're not very proficient in English. They're native speakers of English. But it seems to be that the age at which you learn your second language actually changes or has some influence on how your brain processes the first. And so here's one of the critical differences between the early kind of bilingual from birth bilinguals and the later bilinguals is the later bilinguals already, but if they're learning their second language at age 5, they've already got a fully formed first language pretty much by age 5, by the time they get exposed to their second language. And so this is telling us something about how two languages might get organized if they're being acquired at the same time into one system that's very much engaging some of those left hemisphere classic language regions, or if that language is being acquired later on, in which case there seems to be additional frontal activity, which might indicate additional kind of cognitive demands associated with incorporating a new language, right? So we still have lots of questions about what might be going on, but it's interesting to see that the age at which your second language is learned has an impact on how you process your first, even the one that you speak the best and you're highly proficient in. Okay, so beyond sort of the age of bilingualism, what about the kind of languages you learn? What about the different language pairs you might be exposed to? So we did a study here, same kind of group of readers, same reading task, but we instead just manipulated these different language groups. So we had English and French bilinguals and Spanish English bilinguals, and they were both bilinguals who were bilingual from birth and had reading experience in both English and in Spanish, and English and in French. And so here's why it's really interesting, why we wanted to look at English, French, and Spanish, these three languages. Because these languages kind of differ along a continuum of orthographic depth. And here's what I mean by that. Some languages have a really predictable mapping between letter and sound. They only have regular words. Spanish is a language like that. Some languages have a lot more exceptions, and there's a lot more opacity. English is a lot like that. So in English, you can have, say in the word circus, the letter C can also be the S sound, or it could be the K sound. And so there's kind of some confusion and some challenge around that, whereas you wouldn't have such a thing in Spanish. So these languages, and French is somewhere in the middle. It's not as opaque as English, it's not as transparent as Spanish. So these languages kind of fall along this continuum. And so we wanted to explore, to what extent the kind of orthographic depth of your first language, whether it might have some influence on how you're learning to read. So what we did in our reading task, we actually, in terms of the behavioral results, found no differences in reading accuracy between any of the groups. All kids were reading very accurately these regularly spelled words. For the irregularly spelled words, just the Spanish English bilingual group showed lower reading accuracy, which follows if you're learning to read and your other language doesn't actually have these irregular words, that this might be more of a challenge. And the really exciting thing is that we actually see a mark of this on the brain. So again, I'm showing you that regular versus irregular contrast. And for our monolinguals, no surprise, we have this left inferior frontal activity for those irregular words relative to regular. But for the same age, same reading skill, Spanish English bilingual kids, that same contrast actually produces a different pattern of results in the brain. And we're seeing a relatively more activity in some of these regions that are associated with phonological processing and letter sound mapping. And again, these word types, regular and irregular, would differentially recruit the inferior frontal gyrus and superior temporal gyrus because they differentially rely on lexical access and phonological processing. And so by comparing these specific types of bilinguals, we can see an impact of the typology of the first language on reading. So you might think, well, does this extend into other domains of language? And actually, a doctoral student working in my lab, Danyang Wang, had the same questions, and she wanted to look at cross-linguistic differences in the domain of morphosyntax. And what she did in the study, she actually did this with adults, and she had 3 groups: English monolinguals, Spanish English bilinguals, really English language learners because they were later bilinguals, they weren't birth bilinguals, and Mandarin English. So it showed these 3 groups: English monolinguals, Spanish English bilinguals, and Mandarin English bilinguals. And while participants underwent a neuroimaging language task with FNIRS, so they completed a subject verb number agreement task. Now, so what exactly do we have these participants do? So this is not a reading test, it's just a language task. and participants would see a picture like this of an artist sleeping or two artists sleeping. And they would hear sound, a sentence being spoken out loud, that either corresponded to that picture or not. So if they saw a picture of one artist, and they heard the artist sleeps, they would press a button if this was correct, if the picture matched the sentence. If they heard the artist sleep without the S here, the S marker at the end, and saw this picture, they would mark that as incorrect, as the picture and sentence didn't match. And then they did the same applies for the plural form. So in English, that subject verb number agreement is marked, the verb is marked with an S, and we mark that in the singular form. And so actually these three languages really differ on how they do this. So both English and Spanish mark subject verb number agreement. They have subject verb number agreement, and this is marked in syntax. In English, we mark the singular verb with the S. Spanish actually does the opposite. They mark the plural form with an N, but both languages have this inflectional morphology system. Mandarin does not. Mandarin does not have inflectional morphology. Rather, number is expressed through lexical semantics and specifically through compounding. So actually just putting two words together, rather than adding suffixes or prefixes or infixes like inflectional languages might. Mandarin does this through compounding. Compounding is just putting words together, like snowman, snow and man's meaning snowman. You could do a similar thing in Mandarin to express the plural rather than mark it with an inflection. So Danyang wanted to look at patterns of brain activity across these groups of bilinguals as they were processing this English inflectional contrast. And here's kind of what she found. And I just want to kind of focus us on the activity in the left hemisphere. So let me walk you through some of this. So when we compare the English, the singular versus plural form, our English speakers show a little bit more activity here in the left frontal region. And this is really a typical pattern of results for this type of task in an English native speaker or monolingual. But what's really interesting is that neither group of bilinguals looked like the English monolingual exactly, and they didn't look like each other, right? So it'd be one thing if both bilingual groups looked a little bit different from the English monolingual, but they were the same, right? So you could say, okay, something about just the experience of being a bilingual, of having learned another language, might change how your brain processes that information. But it's really something about the structure of your language that seems to be driving this. So for the Mandarin speakers, when they were processing this English construction, they showed really robust activity in the left middle temporal gyrus, which is a region that we know to be associated with lexical semantic processing. And so when you're doing a compounding process, this is the region that we'd expect to be implicated. And so even when you're processing an inflection in English, we still see some activity that seems to be related to the particular characteristics of how this process works in Mandarin. And in Spanish, we also didn't seem to see the same pattern as we do in English. One of the things that sort of struck us at first is, the Spanish group seems to show more activity for the plural rather than the singular form. And then we realized, well, actually the plural form is what's marked in Spanish, and so perhaps that may be related. So neural activity is a function really of the linguistic properties of the first language. And so we see this in the linguistic properties of the orthographic system when processing reading, the linguistic properties of the grammatical system when we're processing morphosyntax as well. So I'm going to tell you about one more study, so we should have lots of time, hopefully lots of time for questions. And this is work that my doctoral student, Shaklo Nemetova, has been doing. And she's been working with a very interesting group of bilinguals, Bimodal Bilinguals. So in her research, she's looking at deaf individuals who have a cochlear implant. Cochlear implant is a surgically implanted device that stimulates the cochlea and allows for sound, for auditory processing, for sounds to be processed. So she examined deaf cochlear implant users who also learned and used American Sign Language. This is a really incredible group. of people. These were all adults. And they were actually all students at Gallaudet University in Washington in the US. And Gallaudet University, I spent about 2 years there where we were doing some of this work. And it's an amazing place because it operates in American Sign Language. And so it's like any other university campus you go to, classes and students and all sorts of busyness and full of life, except everybody is using American Sign Language rather than speaking a spoken language. Certainly you hear some spoken language, but you would be using sign language there. So it's it's like visiting another country and seeing another country use a different language. It's kind of a little cultural enclave, and it's a really incredible place. So we're really lucky to be able to work there, where we were able to recruit a population of individuals who were using sign language every single day of their lives in their classes and interacting with their friends, but who also had a cochlear implant and had learned English, spoke English, and had some hearing experience through that cochlear implant. And we had these individuals do a neuroimaging task, again, using functional near-infrared spectroscopy. Here's the really interesting thing. An individual with a cochlear implant cannot go into an MRI. It's not safe. So they have a medically implanted device. The MRI is a giant magnet. It's very risky that it might pull some of that surgical device out. They're not permitted to go into the MRI. And so we can't do any neuroimaging research on individuals with cochlear implants using MRI technology. FNIRS, however, is completely safe for these individuals because rather than using magnet, it uses light. And so we just shine light on the brain and measure brain activity using that. And so it's perfectly safe for this population. And so we're really able to get a look into how their brain are processing these different forms of language. So our participants did the same sort of phonemic discrimination task that our babies did way back when. And so what they did was listen to a string of syllables like pa, 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 pa. At some point, if one of those syllables changed to a ba, they were instructed to press a button. So if they caught the difference, if they were able to perceive that difference and that change in syllable, they were instructed to press a button. So pa, 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 ba, pa, pa. If they heard that ba, they pressed it. These bilinguals, these individuals are bilinguals. They speak English, they sign in American Sign Language, they use both of these languages regularly, but their languages span two different modalities, right? So we've got an auditory language, English in this case, and a visual language, American Sign Language. So we would call these individuals bimodal bilinguals. But they allow us to probe sort of really interesting questions about the extent of language organization and how much modality might actually affect it. And one of the things in this population that we observed is a lot of variability in the age at which individuals received the cochlear implants. So some had been implanted really early in life, like 1, 2, or 3 years old. Some got their implant, as children. Some got their implant as teenagers. So there's just a lot of variation, naturally occurring variation in when individuals received a cochlear implant. And therefore had first sort of auditory exposure or exposure to spoken English. And there was also a lot of variability in the age at which they learned American Sign Language. So some had learned sign language right, at the very beginning, in a very early life was their first language. Some had learned sign language when they got to school. Some had learned sign language, as teenagers and so on and so forth. So we sort of had this like natural variability that we were able to leverage in the study. And so Shaka wanted to understand, the kind of bilingualism when you've got potentially early exposure to both of these languages. And so I'm going to tell you what she found. First of all, individuals who received their cochlear implant earlier had better performance on our phonemic discrimination task, but there was no effect of the age at which you were exposed to sign language. And this is actually really interesting and very important because there's a lot of controversy around whether bilingualism might actually hurt or disrupt or delay language development. So if you've got a cochlear implant and you're learning English, might being exposed to another language confuse you, especially if that language is a sign language? Might that actually cause some harm? What we find here is actually no. Like, when you're exposed to another language, there's no negative impact on your ability to discriminate phonemes in the other language. And when we looked at brain activity, actually, for those individuals who had been implanted early on, the younger they were when they were also exposed to sign language, the more activity they had in some of these regions of the brain, the superior temporal gyrus, and middle temporal gyrus that we've already seen. And so it seems to be that early exposure to language, irrespective of whether it's signed or spoken, so this kind of early bilingual exposure, again, across these modalities, is associated with activity in left hemisphere language areas. So with that, I'm going to try to kind of summarize for us and conclude a couple of the points we have from this kind of big tour of all these different bilingual populations. So first and foremost, you can see there's just tremendous variability in this population. What it means to be bilingual really varies, and that definition can be expanded to those who are cochlear implant users who also use a sign language, those who might be learning another language later in life, individuals who learn more than two languages, which we haven't had a chance to talk about here. There's a lot of this kind of interesting variation. And so the neurobiology of how language is organized in the mind seems to be sensitive to the age at which those languages are learned, the linguistic properties of those languages, and that's true across different domains. We include morphosyntax, orthographic processing, at least in the studies that I showed you. The neurobiology of language changes as a function of reading and supports children's reading ability as well. And this seems to extend to all languages, whether they be signed or spoken. So we still have a lot of work to do because we've certainly just started kind of probing some of this variation to try to understand the system a little bit better. So with that, I'm going to stop here because I think I'm at my time. I've so many people to acknowledge and so many sources of funding that made a lot of this work possible, both to myself and some of my mentors. A lot of the work that I showed you was done with my doctoral advisor, Laurent Petito. Some of the work I did as a postdoc with Ken Pugh and Nicole Landy, and some of the work now coming out of my own lab. And some of our, just acknowledging some of the funders that made some of our work in Côte d'Ivoire possible, that I only had a brief opportunity to touch upon. So maybe I'll stop here and see if there are any questions.
Thank you very much for such an interesting lecture. And we have some questions from the audience. And we will try to ask as many as we can before the time runs out. So let's start with the first one. I was wondering if the children who can fluently read prior to 6 years of age have different representation of the pathways. Is it connected with the possible global reading that they were exposed to, or more intense connectome connections?
Oh, okay, yeah. So this is a really interesting question. Okay, so I love this question because all I've shown you here, so here, are just different regions that are active, and we haven't even talked about connectivity. One of the really interesting recent things that we've observed is that for kids, for pre-literate kids, we followed a group of pre-literate kids for a year, right? Like across that transition from not reading formally to going to school and reading formally. Now, lots of kids, the caveat here is lots of kids are, learning to read at home with their parents, and there's all this kind of variation around that. It's conflated with socioeconomic status, and it's kind of an exciting and interesting area of its own. So we're following these readers, kids who are pre-readers to becoming readers. And what we looked at was, what are the predictors of reading when you actually get to school? And so we looked at brains of these pre-readers, and it turns out that the most reliable and the biggest, the most important neural predictor of how well you read a year later when you actually started to learn to read was functional connectivity for language, not brain activity in these different brain regions. So it's not just that these regions are engaged in these tasks, it's that they're working together and that there are these close connections that are taking place between the inferior frontal gyrus, superior temporal gyrus, and regions including in the right hemisphere. And so it's the formation of that network that's actually the big driver. So I'm really glad that somebody asked a question about connectivity, because this is really important and a very exciting area of work. And some of what we're doing now is wanting to understand, to what extent that connectivity might differ between monolinguals and bilinguals across that transition as well. I hope that answers that question.
Thank you for the elaborate answer. And let's go to another question. Many musicologists treat music notation and mental ideation like a language in itself. Do you think this similarity can be seen in the brain activity?
Oh, possibly. Yeah. I mean, look, where the regions that we are implicated are regions that are involved in auditory processing and processing those kind of the rhythmic and that kind of temporal patterns of language, and that's going to be implicated in music as well. Robert Sutori gave a really great talk about some of those things yesterday, and he's got obviously just an incredible program of research around that. I've never done any work in music myself, but I certainly think there's some indication that these regions do serve some of those same purposes, and this is sort of idea that different abilities would be completely independent in the brain. It doesn't really intuitively, from an evolutionary standpoint, make sense. It would follow that our ability to sort of discover pattern, which is what the foundation of language, being able to discover those sound patterns, is also important for processing music. And so those same structures and those same systems have got to be leveraged for both domains.
Thank you for your answer. Let's go to another question. Can early reading be a predictor for better verbal working memory?
Oh, this is a very interesting question. Okay, so reading in of itself actually improves language, right? So I mentioned very briefly phonological awareness. So how your awareness of the sounds that make up your language, your ability to kind of manipulate them and combine them. How will you do that? And we measure that in young kids with tasks like, say cat without the k. Okay, that would be at. So a child that's able to isolate that first sound, remove it, and repeat back the remainder would be one that would score well on a phonological awareness task. So that ability really predicts reading. So you can measure that in really young kids, and those that do better on those tasks are better readers. But as you learn to read, because you're engaging in kind of like letter and sound mapping, reading sort of forces you to tune into and focus on the sounds of language in this really new and deliberate way. So it improves your phonological awareness. And I could see, that kind of benefit of reading, the same sort of reciprocal kind of relationship that we see between phonological awareness to reading, and then reading improving that. Should exist across multiple domains. Well, I have never actually myself measured working memory as a function of reading, but we know that kids with better working memory are better readers. This is one of those really important cognitive components of skilled reading. And then the ability, the kind of working through letter sound mapping kind of in this deliberate way is likely to have some support for that as well. That's a great question.
Thank you very much. I think we have time for at least one more question. Question is, could larger vocabulary size, a sum of two languages, explain the bilingual advantage in reading?
Yeah, so this is a great question as well. I love these questions. So the way we measure vocabulary in monolinguals and bilinguals, this is kind of a really important area in and of itself. So a lot of the time, these claims are made about bilinguals having language delay. And a lot of the time that claim is based on measuring, say an English monolingual child's vocabulary to a Spanish English bilingual child's vocabulary in only English, right? And so their vocabulary is lower, right? Because it's measured in only one language, and there's sort of this discrepancy. So I love that in your question, you actually focus in on the fact that the total vocabulary size might actually be larger. Vocabulary is also like a really important driver, predictor of reading. Tends to become a little bit more important as you get older, when you're no longer really relying on sounding words out letter by letter to the same degree, and you're using more of lexical access. So just a kind of a note around the way we measure vocabulary is in bilinguals really needs to be inclusive. And then whether that kind of larger, we go back to your question. So whether the larger, I kind of forgot exactly, whether the larger vocabulary size, like it's the sum of the two languages, might explain some of the advantage in reading. Quite possibly. There is really a lot of kind of components to that. We know bilinguals do have different vocabularies. Sometimes one vocabulary is tied to a different context, the home, and other vocabulary is tied to a different context, school. And so you sort of acquire kind of a richer vocabulary across that. And knowing that vocabulary is an important component of reading as well, that might certainly account for some of those differences between the monolinguals and bilinguals too.
Thank you for your answers. Unfortunately, we have some more questions, but we're pressed for time.
You are very welcome to email me if anybody has any more detailed questions that stem from the talk. I'm very happy to hear from anybody from the audience.
Yeah, we should forward them to you, and we hope to get such exciting answers like this one. And once again, thank you very much for your time and for your lecture.
Thank you very much. It's been a pleasure.
Yes, and we invite our viewers to another lecture that will take place in about 5 minutes. Thank you very much.
Thank you.